Our topic in this lesson is the derivatives of exponential and logarithmic functions. In this section, we have some conventions that will follow and throughout the rest of the course. Whenever I use the lowercase value e, that's a constant in mathematics, and that constant will be 2.71828. It's an irrational number, it goes on forever. This is plenty of decimals for our purposes, but that's what I mean when I put an e. The natural logarithm of x, ln of x that is defined as a logarithm of base e of x. Sometimes the natural logarithm is just log of x in some textbooks, but we'll use the ln x for us. And log of x we will call the common logarithm, which is a logarithm of base 10. Now, when it comes to derivatives of exponential functions, we're actually in for quite a treat. It turns out the derivative of the base n exponential function is itself. The derivative of e to the x is e to the x. We can't get much better than that. The derivative of an exponential function for any other base is itself. So if that base is a, for instance, it's a to the x times the natural log of a. Still not too bad. And the derivative of the general exponential function is d dx of e to the function u, where it's assumed u is a function of x, is e to the u times du dx. So that's just using the chain rule. So let's prove these and see where the results come from. And I believe I will begin with the proof of the derivative with respect to x of the function e to the x. So this derivative is, by definition, calculated by taking the limit as delta x goes to 0 of e raised to the x plus delta x, because for the limit definition of a derivative, it's your function evaluated at x plus delta x. So e to the x plus delta x minus the function itself, so minus e to the x, all over delta x. So I'm going back to the limit definition here to find out how this works out. Okay, well, first thing I can do is work with some properties of exponentials, in that something raised to a sum can be split up into two separate exponential functions that are multiplied. So this would be e to the x times e to the delta x minus e to the x all over delta x. Now there's a common factor of e to the x in the numerator. I can factor that out. And if you'll notice, this is not a function of delta x. So it's e to the x is not a function of delta x. X is not changing with respect to delta x. So the entire object, e to the x, can be pulled out of my limit, because as far as this limit is concerned, the only variable is delta x. That's the only thing changing. So I can remove that, and that leaves me with this right here. Now this may be a limit that you've worked in the past, or it may not have. This limit can be done fairly easily if we use a table. There's probably some algebra that we can do as well, but I think the table method is probably our best bet in this case. So let's just get the calculator out, and I'll set y1 to be the numerator, and I need to make it e to the x instead of e to the delta x because I don't have a delta x to use, but that's okay. Minus 1, so I've got the numerator in parentheses, and the denominator doesn't need parentheses around it because it's just one term. And what I'm going to do is just make sure my table is set up properly, so second in window, that looks great, so I'll go over here to my table, which allows me to put in values of x. And I want to see what's happening around 0. So if I put in 0.1, 0.01, 0.001, and so forth, I'm getting values that are larger than 0, but getting closer and closer to 0. And it looks like these are approaching 1. If I start with values that are less than 0, but getting closer and closer to 0, it looks like these are also approaching 1. So the limit from the left is equal to the limit from the right, which is 1. So that tells me that this limit is just 1. So this would be e to the x times 1, which is just e to the x. So that establishes the derivative of e to the x as itself. Pretty nice property. Okay, the other thing that I want to prove here is the second statement that said that the derivative of a to the x was a to the x times the natural log of a. In order to do this, so the derivative with respect to x of any other logarithmic or exponential base, what I'm going to do is rewrite this using base e. The way that I'm going to do this is effectively I'm going to let y be the function a to the x. And what I can do is let myself take the natural log of both sides of this statement. And you're allowed to apply any function that you want to an equation as long as you do it to both sides equally, and logarithms are no different. The advantage here, if you'll remember your properties of logarithms, is that the exponent on the a can come out as a constant multiplier on the logarithm. So that gives me the natural log of y is equal to x times the natural log of a. Now, the next thing I can do is make each one of these statements an exponential function of base e. That's fine. And there's a property of exponential functions that e to the natural log of anything is just whatever that argument is. So this just reduces down to y equals x natural log a. So that tells me a to the x is the same thing as e to the x natural log a. Okay, so this is now equal to the derivative with respect to x of e to the x natural log a. Alright, so really all I've done is just change the base of this exponential function. But what that's allowed me to do is change this into an exponential that I already know the derivative of. I just showed that the derivative of something base e is itself, and something of e to the u, using the chain rule, is e to the u, which is this, times the derivative of u. And u in this case is my exponent. So the derivative of u here is just the natural log of a. And to clean this up, we said that a to the x is the same thing as e to the x natural log a. So that means this is a to the x times the natural log of a, which establishes both rules here. So let's see some examples. All right, let's differentiate a few examples here. First, I have y equals 4x e to the x. Now, this is only slightly tricky. You just have to remember that you have two functions of x that are being multiplied. And because that is the case, you need to use the product rule. So what I will do is say 4x is my first function that's being multiplied, e to the x is the second. So the derivative is going to be the first function times the derivative of the second, e to the x is its own derivative, plus the derivative of the first times the second. So that completes the product rule. At this point, any sort of simplification that your teacher wants you to do, go ahead and do that. It looks here like we could definitely factor out 4e to the x from each term, which would leave me x plus 1. And that's about as simple as we can get it. B. F of x equals x squared divided by 3e to the x. In this situation, I have a quotient, so in order to find the derivative, I'm going to need to use the quotient rule. So I'll draw a box off to the side, put my numerator in the upper left-hand corner, and the denominator in the upper right-hand corner. When I do the derivative involving e to the x, that's where the rule for differentiation of exponential functions comes in. But the derivative of x squared is, of course, 2x. 3e to the x, its derivative is just 3e to the x, because e to the x is its own derivative, and then you have a constant multiplier of 3. When I go to form my derivative, I need to make sure I'm multiplying these two corners first. So I would have f prime of x equals 2x times 3e to the x minus x squared times 3e to the x. That all gets divided by the original denominator squared. Now, simplifying here, in the numerator, I've got factors 2 and 3 that can multiply and give me 6x e to the x minus 3x squared e to the x. And in the denominator, that would square out to 9e to the, it's technically going to be e to the x quantity squared, but that's the same thing as e to the x times e to the x, which reduces to e to the 2x. And that's why I wrote that as e to the 2x. Okay, let's go back to simplifying here. Now, when simplifying, the next thing I could do is pull out some common factors from the numerator. In the numerator, I have a common factor of 3, and also a factor of x, and e to the x, which would leave me, in the first term, only a factor of 2, and in the second term, an x. So 2 minus x is all that remains there, and that's divided by 9e to the 2x. And I actually have some things that will cancel. So 3, of course, goes into 9, leaving a factor of 3. But e to the 2x, remember how that's the same thing as e to the x times e to the x. So I have a factor of e to the x in the numerator, and a factor of e to the x in the denominator, leaving just one factor of e to the x in the denominator. And so
my final answer here is x times 2 minus x all over 3 e to the x.
Now we have g of x equals 5 times e to the x squared minus 3x. The derivative here, we're going to need to use the chain rule. And in order to use the chain rule, I need to define the part that I'm using for u. When it comes to exponential functions, you'll almost always want to use u as your exponent. And then the derivative of u is usually pretty straightforward to come up with. In this case, it's just a polynomial, so 2x minus 3. So the derivative of the whole thing, the function g, will be 5, which is a constant. Just leave it off to the side. Then e to the u, so e to the original inner function, times du, the derivative of that inner function. And simplifying, in this case, really just looks like all we can do is maybe rearrange the terms. And there we have it. Now let's take a look at derivatives of logarithms. So the derivative of the natural logarithm, which is ln x, is just 1 over x. Kind of surprising because the natural log of x is a transcendental function and 1 over x is a rational function. It's kind of interesting that that derivative works out the way it does. We'll do a proof and maybe that will help you understand why, but maybe not. The derivative of a logarithm for any base, so if I have log base a of x, it's just 1 over x times the natural log of a. And the derivative of a logarithm in general is the natural log of u is u prime divided by u. So let's take a look at the first one, the derivative of the natural logarithm. So the derivative of the natural logarithm, the way we're going to do this, as we get more and more rules for differentiation, we don't always have to go back to the limit definition. We absolutely could here, and there is a way of proving this with the limit definition, but it's not really necessary. In fact, the way I'm going to approach this is I'm going to let some function y be equal to the natural log of x. Now, whenever you have logarithms, there's always an equivalent exponential form of the equation that you're working with. And so, changing this into exponential form, it would look like e to the y equals x. You may have to go back and start reviewing some logarithms if that's unfamiliar to you, but I'm just taking the base raised to the exponent, which would be y, and then equal to the argument of x. Now, I'm going to differentiate both sides of this equation. So I'm going to take d dx e to the y and set that equal to d dx of x. Again, this is perfectly fine to do. As long as you do the same operation to both sides of an equation, that's perfectly fine. But in this case, I'm doing a derivative with respect to x of a function e to the y. I don't have an x in this. However, y can be written as a function of x, which means I'm allowed to use implicit differentiation on this one. So using implicit differentiation, the derivative with respect to x of e to the y is itself times the derivative of the inside part, so times dy dx. Now that's equal to the derivative with respect to x of itself, which is 1. And that gives me, by dividing by e to the y, dy dx equals 1 over e to the y, but y, we know how to express y in terms of x. Y is the function natural log of x. And it turns out that e raised to the natural log of anything is just that, anything. Algebraically, that should make sense as an argument. It might not fully be understandable geometrically, but at least you have some basis as to where this rule comes from. Now, the chain rule, I'll just assume, because letting this be some function u, all we're doing then is taking the derivative of u in the numerator divided by u itself. So that's just applying the chain rule, so I'm not going to do a separate proof for that. But I do want to do a proof of the derivative with respect to x of log base a of x. So if I have any other base besides e. Well, this one's fairly straightforward. If you recall, there is what's known as the change of base formula for any logarithm. So you can change the base of one logarithm to any other logarithm through this formula. It would be the natural log of the argument divided by the natural log of the original base. And you don't have to go to natural logarithms. I'm choosing that in this case because what that does is sets me up to take a derivative of something I've already proven. So the natural log of a is a constant, which means I can pull that out of my derivative, and I only really need to do now the derivative with respect to x of the natural log of x. And I've already shown that to be 1 over x. So that's where we get 1 over x times the natural logarithm of a. So let's see some examples with logarithms, beginning with f of x equals 5x log base 3 of x. The derivative here will require the product rule. I'm going to call the first function 5x, and then the second function then would be log base 3 of x. So I will start off doing the first times the derivative of the second, which would be 1 over x times the natural log of the original base, which is 3, plus the derivative of the first times the second. So there, I'm finished with the product rule. The rest of it is just a matter of simplifying anything that could be. One thing that I notice is I have an x in the numerator and denominator here. There's also a common factor of 5 at this point. So I could write this as 5 times 1 over the natural log of 3 plus, oops, force of habit, the log base 3 of x. Next up I have y equals x divided by 3 natural log of x, and that's going to involve the quotient rule. So I'll set up my box over here, x in one corner, 3 natural log x in the other. The derivative of x is 1. The derivative of 3 natural log x is 3 over x. These two are going to multiply together first. So when I start setting up my derivative, it's going to be 3 times the natural log of x minus, and this is kind of neat here, I have a x in the numerator here, x in the denominator there. When I multiply those two together, they cancel each other out. So then minus 3 here. Then I divide by the original denominator squared. Alright, so that's your derivative. If your instructor requires further simplification, here's a little bit more you can do. We can factor out 3 from the numerator, and the denominator can be the 9 times the natural log of x squared, and it looks like 3 would go into 9 3 times. So final answer here, the natural log of x minus 1 all over 3 times the natural log of x squared. Right, last one of these. Let's see how this works. G of x equals 4 natural log of cosine x. This is going to require a chain rule, and let's see how this might work out. So the derivative of g, I can choose to put 4 off to the side for right now, and I'm going to do that. So I'm only concentrating on the natural log of cosine x. Effectively what's happening here is I have this inner function, which is cosine x. The derivative of that would be negative sine x. Okay. The natural log function, the derivative of some function u with respect to x is u prime over u. So even though it looks like this is going to be really complex, it actually works out really nicely. This becomes, I take the derivative of cosine, which I've already said is negative sine x, and divide that by cosine x. I don't even involve the logarithm anymore. It's just take the argument, find its derivative, put that over the argument itself, and you're done. I can do a little bit of simplifying here. I can make this negative 4, and then sine over cosine is tangent, but that's about it. We'll conclude this lesson with a very important type of differentiation called logarithmic differentiation. So logarithms have unique properties that allow exponents to be changed into multiplication, division. Multiplication and division can be changed into addition and subtraction. These are very advantageous when it comes to finding derivatives, because addition or multiplication and division require the product and quotient rules in order to find derivatives. If we can change those somehow into addition and subtraction, we don't need to use product and quotient rules. So let's take a look at how logarithms can help us do derivatives. There are properties that are extremely useful. They have lots of properties, but these are probably the ones we're going to use the most here. First, that a logarithm of any base of 2 items multiplied can be split into 2 logarithms added. The logarithm of 2 things divided can be split into logarithms that are subtracted. And if you have an exponent on the argument of your logarithm, you can pull that out as a constant multiplier. So finding derivatives of exponents often requires a chain rule. Multiplication and division requires product and quotient rules. So like I said, if we can change these functions around so that those rules aren't needed, that really gives us an advantage in differentiating very complex functions. So this process will work for any function, but unless the original function is extremely complex, the time involved in converting doesn't really give you an advantage. To differentiate y equals h of x using the process of logarithmic differentiation is as follows. First, take the natural logarithm of both sides of the equation to get the natural log of y equals the natural log of h of x. Like I said before, as long as you do the same operation to both sides of an equation, that's okay. Next, use properties of logarithms to expand the natural logarithm of h of x as much as possible. So any parts of h of x that are multiplied, split those up into addition and subtraction. Any exponents, bring those out as constant multipliers. Now, apply differentiation to both sides of the equation. Use implicit differentiation on the left to get, so the left-hand side is just the natural log of y at this point. The derivative of natural log of y would be 1 over y times dy dx. Then multiply both sides of the equation by that y in order to get dy dx by itself. And finally, replace y with h of x. Let's take a look at an example where this might be useful. Here is a bear of a function if we were going to differentiate this thing as it is. So y equals 3x times the square root of x squared minus 1 all over e to the x sine x squared. Now, this involves a quotient rule, it involves multiple product rules, and multiple chain rules. It really would take an extremely large amount of algebra, long time, in order to get this to work out. This is where logarithmic differentiation is really helpful. So here's what we do. We take this equation and we find the natural log of both sides. And it may seem crazy because we're taking an equation that's already complex enough, and then we're throwing a logarithm at it. Doesn't that seem like it's just making this worse? Well, sure, I can see the point there, but what we can do now is use those properties of logarithms. First, I've got that division bar. So instead of needing the quotient rule, I can rewrite this as two parts of logarithms, or two separate logarithms, I should probably say, that are subtracted. I would no longer need a quotient rule in order to differentiate either one of these. So the quotient rule is out. We don't need it now. Similarly, I can split up each of these separate logarithms again because 3x is being multiplied by the square root of x squared minus 1. I can split that up into two logarithms that are added together, and I will go ahead and make this to the 1/2 power instead of a square root. Same thing can happen on the other side. This would be the natural log of e to the x. And be careful here because when you split the, actually I'll tell you what I'll do. I'll put this in parentheses and then say that it's added, but that negative distributes. So natural log of sine x squared. Okay, now I'm going to simplify exponents. So this is the natural log of 3x. That's about all I can do there. Plus, instead of a square root, I can make this 1/2 of the natural log of x squared minus 1. That's pretty good. This is minus the natural log of e to the x and minus 2 natural log sine x. Okay? And the only other thing that I can do that's a little bit better is, I'll just do it real quick here. The simpler you can make this thing, the better. natural log of e to the x can be just written as x. Okay, now this is all still equal to the natural log of y. This may look more complex to you, but in terms of differentiation, it's going to be a lot simpler because none of these terms require product rules, quotient rules, or even chain rules at this point. Well, yeah, technically it uses a chain rule for the logarithms, but that's much simpler than most chain rules. What I need to do next, differentiate both sides of the equation. So I'm going to differentiate with respect to x the natural log of y. And I'm pointing that out because I want you to know that I have to use the chain rule there. Or, I'm sorry, you have to use implicit differentiation there. On the other side, I'm differentiating each of these term by term. The derivative of the natural log of 3x is just the derivative of 3x divided by 3x. In the next term, the derivative of the natural log of x squared minus 1 is the derivative of x squared minus 1 over x squared minus 1. These are pretty easy to do, you have to admit. The derivative of x is just 1, and the derivative of the natural log of sine x would be the derivative of sine x, which is cosine x, and then over sine x. Okay, now this left-hand side, I've got the derivative with respect to x of the natural log of y. If I'm differentiating a function of y with respect to x, then what I can do is use implicit differentiation, go ahead and differentiate it normally, but then multiply by the derivative of the inside part. Now, this is all going to basically stay the same. I'm going to make a couple of quick simplifications. Like for instance, 3 over 3 I'm going to cancel, 2 and 2 I'm going to cancel. So this will be 1 over x plus x over x squared minus 1, minus 1, minus 2. Cosine over sine is cotangent. So I'll make some simplifications there. Now at this point, all my differentiation is done. So as bad as that looked like it was going to be differential-wise, wasn't all that bad. I do, however, need to multiply this y to the other side of the equation in order to get the derivative by itself. More than anything, this is just a bunch of rewriting the same things over and over again. And as you do a couple of problems, you'll probably not write down as many steps as I am right now. So dy dx equals, so it's y times all of this stuff. Y is my original function. I need to go ahead and substitute that in for x and call it 3x times the square root of x squared minus 1 all over e to the x sine squared x. So I'm just replacing y with what it was originally. That's always going to happen in this logarithmic differentiation. And then these things I will just copy back in. I think I'm going to put the cotangent first because usually constants come at the end. And there you go. As far as simplification goes, this is probably as simple as you want to make it. You could potentially combine some terms in the inside of those parentheses. I wouldn't multiply the 3x square root of x, that whole part on the outside of the parentheses in. I think it would just make things a lot more messy than what they are. So this is fine. Alright, now the reason that logarithmic differentiation is so important is not that it can allow us to differentiate such complex functions. That is really helpful, but it's not the reason why it's so important. The reason why it's so important is that it's actually the basis of the power rule. We've kind of come full circle here because we started derivatives rules with the power rule, and here we're kind of ending it with the proof of it. Let's talk about this. So the previous proof that we did for the power rule really is only valid for positive integers. And the reason is we used the binomial expansion theorem in order to expand terms out. It was a long proof. It wasn't very attractive looking. We had a whole bunch of dots in between an infinite number of terms or a finite number of terms, but we didn't account for them all. So it was kind of based on a little bit of stuff that wasn't very solid mathematically. It works, but there's better ways. We also would like to expand it to know that we can use the power rule for negative exponents. We've been doing that, but it wasn't formally established in the past. Neither were rational exponents, so fractional exponents. They really weren't contained in that rule. But then the question persists of, what about irrational values? So these questions remain. How do we know the power rule works for negative and rational exponents? And does the power rule even make sense for irrational exponents like the square root of 2? To be honest, what does it even mean to evaluate something like 7 to the square root of 2 power? You can put that in your calculator, and it will give you an answer by, say, 7 raised to the square root of 2 power. Look at that. It gives me an answer. The square root of 2 is about 1.4142, and so what does that mean? Like, how do I know that 7 to the 1.4142 is 15.672? Where is this number even coming from? Let's take a look at where this number is coming from. So let's say, for instance, instead of treating this as an exponent, let's treat it as a limit. So let's take a look at it as the limit as x approaches the square root of 2 of 7 to the x. Because 7 to an exponential function x. This is fine. We can handle this. Just now we have to approach the square root of 2. So how do we approach the square root of 2? Well, if we're going to do this limit with a table, for instance, we could do something like 1.4. Okay, so if I do, let me write down the approximation for the square root of 2 so I don't forget it. So 1.41421, and that's probably more than enough. All right, so if I take 7 raised to the 1.4 power, I've got 15.25. So 1.4 is a little bit less than 1.41421, and 15.245 is a little bit less than 15.672. If we get closer and closer to this value, the square root of 2, and the way I'm going to approach it is by increasing the number of correct decimals. That's how we'll do it here. So 7 raised to the 1.41 power, 15.54, and 7 raised to the 1.414, it's 15.67, and I'll do one more. So 1.414 1.4142. So 7 raised to the 1.4142. So 15.67. Okay, now the original answer we had, 7 raised to the square root of 2, was 15.6728. So we are on the right track here. We're getting closer and closer to this value. But how do we know it's that correct value? How is the calculator coming up with it? Is it doing a limit every single time I want something like this? The answer is no. It's actually got a better way of doing these things. Suppose there's a function y equals 7 raised to the square root of 2. If I take the logarithm of both sides of this equation, I have the logarithm of y equals the logarithm of 7 raised to the square root of 2. Or the natural log of y equals the square root of 2 times the natural log of 7. That looks like 0.7, sorry. The natural log of 7. Square root of 2 is an exponent. It can be brought out as a multiplier for my logarithm. Now, I can make both sides of this equation exponents raised to the base e. E to the natural log of y is just y. So I've effectively come up with a way of rewriting 7 to the square root of 2 in terms of exponents, exponential functions, and logarithmic functions. Let's see what happens. E raised to the square root of 2, square root of 2, times the natural log of 7. If everything goes well here, I should get 15.6789087. Exactly the same thing that the calculator got when it did 7 raised to the square root of 2. In fact, this is how the calculator is coming up with that value. It's rewriting it in terms of logarithms and exponentials in order to do this. So the natural log of 7, there's a function that can tell you natural logarithms. Square root of 2, there's a function that can give you square roots as well. Once you get those two numbers, you're just multiplying. So you're not raising something to a irrational value, because how strange is that? You have, say, 7 to the second power. That makes sense. That's 7 times 7, which is 49. 7 to the 1/2 power. That's a little bit weird, but we've kind of established those to be square roots. 7 to the 3/2 power is also a little bit strange, but we've effectively said if you cube 7 and then take the square root, that's how you evaluate that. So any rationals can be done. But if it's just a decimal value, this is what you have to do. You have to change things into exponentials and logarithms. Now, let's go on to the next part of this. The next part tries to answer something like, what happens if we try and use the power rule on these irrational values? Could I, for instance, take the derivative of x to the pi power and call that pi times x to the pi minus 1? Is that a valid statement? Well, let's see what we can find out. Let's go back to the power rule. The power rule is the derivative with respect to x of x to the n is n times x to the n minus 1. We know this is true for positive integers. We want to know if this is true for all types of real numbers n. So let's try it. Let's see what happens if we just let y equal x to the n. N can be any kind of real number. We're going to evaluate this with logarithms. So I'm going to use logarithmic differentiation to come up with this answer. natural log of y, when I differentiate that, it's going to be 1 over y times dy dx. But the other side, I can do some simplification before I get to the derivative part. I've got n, which can pull out as a common factor. So here's what I have so far. Now I'm ready to differentiate. Derivative of the natural log of y is 1 over y dy dx. The derivative of n times the natural log of x is going to be n times 1 over x. These are so far all based off of rules we've established for logarithms, and none of them require that n has to be a integer or anything like that. N can be any real number at this point. To get dy dx by itself, I need to multiply both sides by y. So then I have y times n times 1 over x. But the function y, we said, was x to the n. So this is x to the n times n times 1 over x, or x to the n over, we could say x to the first power if you like, x to the n over x to the first. This has a common base, which is x. So I take x to the n minus 1 times n. So that establishes my power rule for any type of exponent, any real number. And that's a much more concise power rule proof than what we had before. This logarithmic differentiation is extremely important to us. So now, in terms of this question right here, yes, if we want to do the derivative with respect to x of x to the power pi, we can absolutely do that. It's pi times x to the pi minus 1. And that's our answer for that derivative.